First section of the second workshop of this program. And our first speaker for the workshop will be Aidan Sims, and he's going to talk about the recovering dynamics from dynamical construction.
Thank you. So guess I'll start by thanking the organisers very much for. So I've been here for 2 weeks, and I'm here for the next 2 weeks, and it's been fantastic. So thanks for the opportunity to speak here, but also I particularly would like to, and specifically thanking Fen for the immense work that she's done organising this whole program. I'm very grateful to be here. It's been fantastic, really good for me mathematically. So thank you very much. Okay, so yeah, I just want to talk about I guess this idea of recovering dynamics from C algebraic constructions, and I just want to talk through a few different sort of instances of it, and maybe sort of explain what I'm trying to do with it. I guess maybe the writing's a little bit small, so if it's invisible, I can make the thing bigger. It just won't be quite as seamless. So please let me know if I really need to do that. But so I guess I'll start by mentioning. So basically, the idea of this for me came from Robin Dealey gave a talk some years ago that I was at, and he talked about what he called the C-star game. And maybe we should only call it the C-star game amongst friends, but we're all friends here, so I can call it that. But you know, the one thing that we do with C-star algebras is we take some other object of interest, we construct a C-star algebra from it in a natural way, and then we ask ourselves, what does the C-star algebra remember about the object? Maybe also, what does it forget, and what new sorts of, I guess, equivalences between objects of dynamical nature come from, you know, what collapses when you associate a C-star algebra to it. So that's sort of somehow the C-star game is you take an object of interest, you build a C-star algebra from it, and then you compute some things, some invariants, maybe K-theorem, maybe the primitive ideal space, maybe some K-mesh states, I mean, various bits of C-star algebraic information, and then you ask, what does that tell you about the structure of the object that you started with? Yeah. Okay, so that was Robin's C-star game, but then so basically the question is, how much does the C-star algebra of a gadget remember about the gadget? Yeah. Okay, but okay, so what's an example? An example would be you take X, a locally compact Hausdorff space. H is a locally trivial line bundle over X, or maybe a locally trivial vector bundle over X. Sorry, that's a righto. And then I could compute, so then I can build the continuous field of algebras, C-star algebras of compact operators on the fibers of that bundle. And that's going to be a continuous trace C-star algebra. And then I can compute its d-smeared to a D invariant. I could compute the invariant of the C-star algebra. And then I can ask, what does that tell me about the bundle I started with? Well, it tells me something about it up to sort of stable isomorphism, roughly speaking, right? So it doesn't tell me exactly what the bundle was, but it tells me quite a bit of information about the bundle. That would be an example. Yeah. Okay. I want to modify the question a little bit to what I'm going to call the reconstruction game instead. And the reconstruction game is a bit different. So the rules are different. In the C-star game, you build the C-star algebra, and then you have to work with that, and you find out what it does remember. So I'm going to change the rules, and I'm going to say in the reconstruction game, I build the C-star algebra, and then I'm allowed to throw some extra C-star algebraic data in. So I'm allowed to look at how I built the C-star algebra and say, well, this sort of part of how I built it is important. I'll throw that in as well as an extra bit of data in my C-star algebraic toolkit. And I'm going to ask myself, how many extra bits of C-star algebraic data do I need so that I can just recover the gadget completely? Right, so I start with my gadget, I build the C-star algebra. How much extra stuff do I have to remember so that I can recover the whole thing? And the point is, for me, that really I'm still focused on Robin's idea, or the idea that Robin articulated. I'm still focused on, I want to know what C-star algebras can tell us about the stuff that we model with them. But sometimes thinking about this can help to understand that. So let me give you an example. Sorry, I'm just going to make it a bit bigger so that hopefully we can see it. Apologies. Maybe that's a little bit better. It's still a bit pale, but okay. So for example, I take a finite 0, 1 irreducible non-permutation matrix. We all know where this is going, right? I could build a shifted finite type from it then I could build a Diacono Renault groupoid from that, and then I could build a C-star algebra, or I could take the quick route and just build a Kunz-Krieger algebra. Either way, I would get the same C-star algebra, right? Then I could compute the K groups, and I would find that the K0 group of that C-star algebra remembers the flow equivalence class of the matrix up to the sign of a determinant, so up to a Kunz-Weiss operation on the graph, which Mikhail proved. But I don't quite remember everything about the flow equivalence class of the shift space, right? But then sorry, Matsumoto and Matsui realized that if I take the long way around, so I build a groupoid and then build the C-star algebra, and in addition to remembering the groupoid C-star algebra, I remember where the Cartan subalgebra is inside it. So I remember the abelian subalgebra corresponding to the functions on the unit space. That little bit of it, well, maybe it's not a little bit, that additional data is enough to recover the flow equivalence class of the shift space completely, right? So by changing the rules a little bit, by adding a little bit to the data that I'm allowed to remember, I can recover exactly what the shift was. Okay. Oops. Okay. All right, so I want to talk about basically 3 more examples of that sort of idea where I take some information, I take some dynamical or topological data, I build a C-star algebra from it, remember a bit of extra C-star algebraic information and see what I can recover, try and recover the original object. It's a lot of fun. Okay, so my first example is really the example that we just saw, but I'm going to try and push the idea a bit further. So we're talking about groupoids. So suppose that I start with a Tal Hausdorff groupoid and a twist over it. Well, then Kumjian and Renault between them tell me how to build the C-star algebra of the twist. Yeah. And then I might remember, as we did on the previous slide, where the diagonal sits inside it. And then it turns out that, and I'm not going to worry too much about, I mean, I can recover the twist, I don't worry too much about it in general, but right now I can recover it. Turns out that I can recover all of the groupoid data that I started with from those 2 bits of information, right? And this has been a sort of an idea that's been attracting a lot of attention recently. So what's the idea? How does this work? Well, the normalizers of the diagonal. So I'm writing A for the C-star algebra, the big C-star algebra, D for the abelian subalgebra. The normalizers, they're just elements that conjugate the diagonal back into itself. They define little partial homeomorphisms of the spectrum of the diagonal, right? So each normalizer n defines a partially defined homeomorphism from the support of the function n star n to the support of the function n star, basically because if you conjugate by the partial isometry in its polar decomposition, you get a little you get an isomorphism of commutative C-star algebras, so it has to come from homomorphism spaces. All right. And then you just build, as Mark said, I think in the first week, you just build the groupoid of germs of that action. You've got an inverse semigroup now of partial homomorphisms. You build the groupoid of germs of that inverse semigroup, not the Patterson groupoid of germs, like just the honest germs of these functions as continuous maps on the space. And what you get back is the groupoid that you started with. And Anna pointed out the other day, sorry, this is illegible, but Anna pointed out the other day that I can write down what the equivalence relation on germs is by saying that n and m are equivalent at phi if n times d is equal to n times d prime for some paired d prime. Now I want to say where d and d prime are both non-zero at phi, but the way I'm going to say it is by saying that d star d prime is non-zero at phi. So I'm going to put it together in one bit of the data. Because then the point is that the twist is also recoverable, and it's the germs but with phase. So all I need to do is add a little bit of extra data that I remember. So I remember the phase difference between d and d prime by asking that d star d prime is positive under phi instead of just non-zero under phi. Right? Okay. I'm showing you that because what I want to do is push this idea a little bit further, and we're going to find out that, okay, if I want to go a bit further, maybe I can't use that that nice description in terms of phases, but I can still use the same sort of fundamental idea. So, what if G is not a principal groupoid, topologically principal groupoid? What if there's too much isotropy around? Well, in that instance, there's an obvious example that says that I'm not going to be able to do this in general. Because I take my groupoid to be a group. Let's use the integers because it's the simplest group I know, right? I think the integers is simpler than the two-element group because there's no relations. Okay, so I take the integers, regarded as a groupoid, that means it's got one unit, so the diagonal subalgebra is just the multiples of the identity. Yeah. So it's pretty hard for something not to be a normalizer. You know, I mean, I just need a function that's unitary to conjugate one back to itself. So it's just functions from the circle to the circle. That's all of the normalizers. There's a whole lot of them. What are the germs of those? Well, there's only 1 point, so they're not moving it anywhere. So the groupoid of germs collapses. Right? You've just got the group with one element when you build the groupoid of germs of that action. Okay, so we can't use the same approach there. But I would like to be able to recover. I mean, okay, maybe this is a trivial example, but I'd like to be able to recover groupoids where there's lots of isotropy. This is the canonical example. So, okay, maybe you're discouraged by this, or maybe you think, maybe I can do a little bit better. What if I remember? So maybe I just need to modify how I reconstruct the groupoid. So maybe it's worth remembering that the inclusion of Z into its C-star algebra has a left inverse. Like I can undo it if I remember classes in K1, right? So the map that sends U to its K1 class, right, which is in K1, which is isomorphic to Z, that's sort of a left inverse. That is a left inverse for this inclusion. Yeah. So maybe I want to say that two normalizers are equivalent now at the only possible point in the spectrum point that I can worry about. If when I take n star n, so let's just scale them so I get a unitary. I take n star n, that's going to be give me a unitary. I ask what its K1 class is. If it's a trivial K1 class, maybe that's what I want to do. So now I'm just saying two things are only equivalent if they have the same K1 class. Well, that sounds all right, and it works fine for Z. But if I replace, say, Z with the rank 3 abelian group, I'm going to be in trouble here because now there are too many unitaries. And now there are too many K1 classes because when I pair the bot projection with one of the generating unitaries, I get an extra unitary that sort of doesn't come from something in the group. Okay. So maybe we're still a bit discouraged, or maybe we're Tokyo. And if we're Tokyo, then we say, well, no, we can do better than this still. So Tokyo has suggested, why don't we instead use the fact that Z going into its C-star algebra, I mean, okay, we just saw it has a left inverse, but there's another way to articulate it. Its left inverse is given by the map that sends a unitary U to its class in the unitary group of the C-star algebra, no matrices around, modulo the connected component of the identity, the homotopy class of the unitary right? So by U naught, I mean the connected component of the identity in the unitary group. Okay, so maybe we say now two normalizers are going to be equivalent at the only point there is to evaluate that. If when I take n star n, scale it so I get a unitary, and look at its homotopy class that's in the connected component of the identity. That's going to work for basically any torsion-free abelian group, because torsion-free abelian groups all have this property that they are the equivalence classes of those unitaries modulo the connected component of the identity. Okay. And so the construction, so this was in a paper with Torque and Efren Ruiz and Mark Tomford some years ago. And the construction is you do exactly this. So you take, and now you just do this in a groupoid. So you take a groupoid where the interior of the isotropy, so that's all the things that have the same range in source, but the interior, the topological interior of that, you ask if that's torsion-free abelian, fiber-wise. Then you look at so you remember where the abelian subalgebra is, and you look at its relative commutant. So you look at all the things that commute with it. Okay, so that should be the image of the C-star algebra of the interior of the isotropy, which we know decomposes as a continuous field of C-star algebras of the groups in the interior of the isotropy. So it's a big continuous field of commutative C-star algebras. And now I could ask,
the two normalizers are equivalent at the point phi. So it's always going to, they're always going to have to be at the same point. So they're equivalent at this point phi if they have the same germ at phi, and when I evaluate n star m at phi, right? So I look at that element of this continuous field of C-star algebras, it's in the connected component of the identity in the general linear group of that C-star algebra, which is the same as saying if I scale it to unitary, I get something in the connected component of the identity in unitaries. And then the theorem is that we win the reconstruction game, right? So I can recover the groupoid that I started with from that C-star algebraic data using this construction. That's the idea. Okay, and just a remark, so this is why I like playing this game, because this construction works anytime I've got, I mean, I can do this construction anytime I've got a C-star algebra and a sigma unitable abelian subalgebra. So what is this groupoid when the C-star algebra I started with is not a groupoid C-star algebra? And how much does it remember? Like what is that a useful invariant for a pair of C-star algebras? I don't know. That's a question I want to ask. Yes, sorry.
What is the rank of the general linear group? What is that? GLN?
Oh, sorry. It's I mean, when I say GL, I really just mean the like invertible things. I just mean the invertibles. Sorry, I should have just written that in. Okay. But so there's an exclamation mark and there's a question mark. So that was the theorem a few years ago, and then Anna spotted a problem. So Anna spotted an issue with what we've done. And I wanted to talk about this because actually the resolution of the problem turned out to be interesting in its own right. So turns out that the assertion that the relative commutant is the image of the C-star of the interior of the isotropy is trickier than we thought it was. Like we thought we'd proved this, but there was a gap. So it's clear, excuse me, it's clear that the norm closure of the continuous compactly supported functions on the interior of the isotropy is contained in this relative commutant, but it's not clear the other way around. We had sort of missed something there. And we needed to try and fix that. So I wanted to just talk a little bit about how you fix it, because I think it also brings in an interesting idea. That's to do with this question of intermediate subalgebras in groupoid C-star algebras and deciding, when the functions supported on some open subgroupoid are the same thing as the C-star algebra of that subgroupoid. So we need to know that if the interior of the isotropy in some groupoid is abelian, then this relative commutant is the same as the image of the C-star algebra of the interior of the isotropy. And it turns out that the key thing you need to know then is that if I've got an element of the C-star algebra, which I can always think of as a function on the groupoid, and if that element of the C-star algebra is supported on the interior of the isotropy and it vanishes on the fibre over x, right? So it's 0 on the fibre over x as a function. I want to know that that's the same thing as saying that it's in the ideal generated by functions on the unit space that vanish at that point x. And that clearly should be true, but lots of things clearly should be true. It turns out that it was trickier than we thought. Okay, so how are we going to go on? So we thought we had an argument that didn't work. How are we going to try and fix this? I kind of think this little idea is a neat idea that I would like to see how far it goes. So I need to know, so I mean, it boils down to this. I need to know that if I've got a compactly supported function on the groupoid, and when I restrict it to the closure of the interior of the isotropy, which is a weird thing to do, but I'm going to do it over some point. If I restrict it to the closure of the interior of the isotropy over some point, I get an element of the reduced, well, or full, it doesn't matter because the isotropy was abelian, or the interior was. And so the closure of it is as well. I get an element of the C-star algebra of this group, which is a discrete abelian group. Suppose the norm of that in that C-star algebra is small, then I'm going to need to know that when I restrict the same function to nearby fibres in the interior of the isotropy, I don't need the closure now, the norm is also small. That's basically what I need to know to do this approximation. Because then I get a nice uniform bound on how quickly things are going to 0 near a point, and so I can sort of rig up a appropriately chosen approximate identity in here and make sure that when I multiply by it, I converge to the element that I first thought of. How do I do that? Well, that seems hard, but then you realise, and this is kind of cool, that if I take a compactly supported function f, take its support, so the closure of the places where it's non-zero, intersect it with a fibre of the closure of the interior of the isotree, I get a finite subset of an abelian group. So it generates a finitely presented group, because finitely generated abelian groups are finitely presented, right? Generate something, we know what the fundamental group, the theorem about finitely generated abelian groups looks like. So it generates a finitely presented subgroup. So I get a bunch of generators and a bunch of relations, and the relations basically say I've got some family of elements sitting in this fibre of the closure of the interior of the isotree, and when I multiply them raised to the right powers, I get a unit in the groupoid. All right, but this is an Untitled groupoid, so every one of them sits in a bisection. I can put bisections through them. And if the product of the bisections is a unit at X, it's got to be units near X, because the unit space is open. Yeah. So because the unit space is open, if I choose bisections going through these gamma i's, I get a product of bisections that locally lives inside the unit space. Yeah. What does that mean? That means that the relations that I wrote down in the fibre I was interested in also hold in the fibres nearby. Well, I started off with a group given by generators and relations, presentation of a group. Nearby, I've got something, generators satisfying the same relations. So I get a homomorphism from the group that I had generated in the fibre of the closure of the interior of the isotree X into nearby fibres of the interior of the isotree. Well, not into, but to groups in the nearby fibres of the interior of the isotree. And if I've got a homomorphism of groups, then I've got a homomorphism of C-star algebras. The homomorphisms of C-star algebras are norm decreasing, and that gives me the norm estimate that I needed. Just kind of a cool trick. Okay, so the upshot is the theorem, fortunately, was correct as stated, even though the proof needed a little bit. Okay. So that was my first example of this reconstruction game. The other two examples are much shorter. Got about 5 minutes left, and I'll tell you about those. Okay, but a couple of corollaries. So why do I like this result so much? Why did I really want to fix it? So for example, it means that you can characterize stabilizer preserving or continuous orbit equivalence of Diaconou-Renault style dynamics. So irreversible actions of n to the k on arbitrary spaces in terms of diagonal preserving isomorphism of C-star algebras. And also, basically, the Boyle-Tomiyama theorem works for any action of Z on any space, and the same decomposition works, right? So you've got two actions of the integers on two locally compact Hausdorff spaces. Then the cross products are diagonal preserving isomorphic if and only if the two actions decompose into a conjugate piece and a flipped conjugate piece. Yes. Okay. So my second example is Hilbert modules over community C-star algebras. This is work of a student of mine, Rodrigo Frasino. So we're all sort of familiar with Takeshi Katsura's construction. You start with a topological graph E, you build from it a Hilbert module. From that, you get a C-star algebra called OXE, and Takeshi used that construction. I mean, I believe his motivation in particular was he wanted models for all Kierkegaard algebras, where he could control where the position of the unit was. Okay, so Rodrigo's theorem, and this is related to previous work, and I should mention in particular Davidson and Reuter and Davidson Katsoulis, and also Adam Doron and Søren Eilers and Shirley Geffen. So what Rodrigo proved is that if I start with any regular C-star correspondence, so that just means the left action is bicompacts and injective, over an abelian C-star algebra, I can play this reconstruction game, and I can recover the correspondence, the original starting data from C-star algebraic information, and the C-star algebraic information I need consists of three things. So I take the Toeplitz algebra of the correspondence, I take the gauge action on that Toeplitz algebra, so I'm thinking of it as a graded algebra over the Z. And then in addition, I remember where the coefficient algebra is in the Toeplitz algebra. So it's a little bit like remembering where the diagonal is in a group C-star algebra. And what's the key idea here? So it's a different approach, but you know, it's a different sort of key idea, but yeah. So how does it work? Well, this action gamma gives me an action of the real line just by exponentiation. I can compute the ground states for it. It turns out that the ground states are a nice Choquet simplex. It's the same thing as the KMS in the infinity states here. And then you prove that there's a unique multiplier projection of the Toeplitz algebra with the property that when I take the GNS representation for any one of these extremal ground states, I get a rank 1 projection out of it. So it's literally rank 1. And when I evaluate the extension of the state at the projection, I get the number 1. And somehow what's really going on here is this is a rank 1 projection that has maximum value under any KMS state of temperature increasing towards, or inverse temperature increasing towards infinity. All right, so I can pick out some projection that's sort of fiber-wise is minimal. And then it turns out that projection, I mean, you just prove that projection is, so inside the Toeplitz algebra, there's a copy of the compact operators on the direct sum of tensor powers of the module. And this projection is the projection onto the bottom sum end. So you're able to pick out that projection onto the bottom sum end from the C-star algebraic table that we remembered. And then you convince yourself that if I multiply x on the right by that projection, I get a Hilbert module over A. T of x on the right by that projection, I get a Hilbert module over A, and it's the module that I first thought of. So I can recover the Hilbert module. That's how we win the reconstruction here. I guess the corollary then for Rodrigo was if I take two regular topological graphs and this C-star algebraic data is the same, then the graphs are locally conjugate. It's if and only if they're locally conjugate. So they're locally the same. And if the vertex space is 0-dimensional, actually you can do 1-dimensional, but you can do it really explicitly if it's 0-dimensional. If the vertex space is 0-dimensional, then that's the same as the graphs being isomorphic. Otherwise, it's not so clear whether local isomorphism is the same as isomorphism. And it turned out that that was a question that that Ken Davidson and Elias Kasilis had asked some time ago. Is it true that local conjugacy is the same as conjugacy? And Rodrigo was able to use these ideas to see that one way to try and answer their conjecture would be to try and just find a non-trivial vector bundle over a compact space where you can write down the permutation, the transition functions just as permutation matrices. And I believe that there's been some progress made now on answering the question using that idea. Okay. That was my second last example. So the last example I want to talk about very briefly is amplified graphs. Just one more example of this reconstruction game. And I guess I'm just trying to advertise that this sort of idea of trying to reconstruct things, there's lots of ways you can go with it. So countable directed graph is called amplified if the only time there's an edge between two vertices is when there are infinitely many edges between two vertices. And this is like a good toy class of examples for trying to understand some structured results because they're easier to work with. They're quite regular. It's easier to work with than general graphs. So Bates, Honrayber, and Szymanski told us how to build a C-star algebra from an arbitrary graph, like with infinite edges, and sources and so forth. You can compute the ideal structure, and when you do that, that will tell you something, at least in the case where it's amplified, that'll tell you something about the strongly connected components of E in terms of the ideal term. Okay. So the theorem is if I take two amplified graphs, then those graphs are isomorphic. They're the same graph if and only if, so I can remember the graphs using C-star algebraic information. They're isomorphic if and only if the C-star algebras with the gauge actions are the same. Actually, you can do better. That's the same as saying that the stabilized C-star algebras with any action that you get by taking the gauge action and tensoring it by something that's just conjugation by a unitary. Those are the same. And it's really just the same as saying that the equivariant K0 groups of the two C-star algebras for their two actions are the same. And the key idea here is to use that correspondence between ideals and hereditary sets. So what you do is you check that when the graph is amplified, the hereditary sets that have a unique predecessor in the ordering on hereditary sets are the ones that it's generated by our vertex in a skew product graph. So you have to take the skew product graph, but you can take the skew product graph because you remember the gauge actions. So now the ideals of your C-star algebra with unique predecessors, so the cross product C-star algebra by the gauge action, tell you the vertices of the skew product graph, and then you just have to do some combinatorics basically. So you do some combinatorics to identify one level in the skew product graph amongst these ideals. And also to see that by applying the shift map that you get from the gauge action together with the ordering of ideals, you can recover connectivity in the graph. And so you just by hand rebuild the graph. All right, I think that's all I had to say. So the consequence is that Hazrat's conjecture, that's another class of graphs where we can sort of verify Hazrat's conjecture, which is neat. I think that's all I had to say. There's some references the various papers that I talked about here. Everybody wants to have a look at, but that's it. Thank you.
You know an example of two amplified graphs where the algebras are the same, but the gauge actions are different?
That's a really good question. I don't know one. I know Efren's been trying really hard to put one together, so I think he doesn't know one either still, but he would certainly like to. Yeah, good question. It's also not clear whether you can deal with more general sort of actions on the stabilization. It's hard to know.
Any other questions?
So for these amplified graphs, we should have like lots of automorphisms, so you just commute, for example, the edges.
Yeah.
So you have S infinity acting on the
Yeah.
edges. Does that induce anything interesting on KP or?
I don't think it, I think it is that sort of action is just trivial on K theory, I think, because all of those, I mean, all of the classes that you're moving around are going to be equivalent.
Right, yeah.
So I don't think it actually does anything that you can see in K theory. No.
No. Thank you. Thanks no further questions. That's the same.